Hello. This is your teacher. I am making you this video because I am currently not in the southwestern part of Virginia. I am actually in the northern part of Virginia. And I was also on Virginia Tech's campus earlier today doing grown-up things like interviewing for jobs. So anyway, I couldn't be with you today, but I didn't want you to lose a day of instruction because we already had all those wonderful snow days. So I am going to teach you from afar. Now, I'm going to try a few interactive things, and I would like you to participate, even though I'm not here to tell you to participate. So I'm telling you, I expect you to participate, and I better hear from the sub that you are participating. Okay, so when I say pause, I'll say ready, set, go, and that's when you're going to pause the video. And then when you're done, when you've done your discussing or you've tried a problem, then you're gonna push you'll push play again, okay? So you ready to go? Alright, so today we're talking about something super fun. Okay, here's the earth. Round. Dang, that's a nice earth, you might say. But that's not what we're talking about, so that's very unfortunate. I'm just showing you what pretty pens I have. We are talking about something mildly scientific today. It's actually quite scientific. Scientists use it a lot. It is called scientific notation. Okay? And what's great about scientific notation is it lets us write really huge numbers, like 56, I don't even know what size this number is. It's big. I don't really want to give it a name. We can take all these zeros and we can pack them into one little thing. 10 to the 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 10 to the 15th, right? And then we just multiply by what's on the front, so 5.6. So if we want to write up an official definition of scientific notation, which I would hope you actually kind of know because it's been in your SOL since you were in 4th grade, it is a times 10 to the n, where a is a number that is between 1 and 10. So that means it can be equal to 1, it can be bigger than 1, but it can't be less than 1, and it can't be 10 or bigger. Okay, and then n, the exponent on 10, and this is always 10. It can never be anything other than 10. It has to be 10. But the n has to be an integer. So that means positive and negative whole numbers. Okay? So, we have that. Glad we got that. So, the function of scientific notation is to condense these big and very small numbers. So, what I want you to do to start off is I just want you to fill out a little chart for me, okay? So, nice and thin. Alright, here's your chart. I want you to have n on one side, and I want you to have 10 to the n on the other side. So I want you to do -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, and 5, okay? So I want you to do that. I want you to fill out the 10 to the n side here, okay? And so, when I say go, pause it, and then after you pause it, I'll come back to you, okay? All right, so go ahead, pause for about a minute, all right? On the count of 3, 1, 2, 3, go. Hey, welcome back. So I went ahead and filled out the chart so you could check yourselves. But basically it should be this nice, pretty looking thing, kind of makes a half an hourglass. But all it's doing, really, is if you were to plug these into the calculator, it's just moving your decimal, right? So it starts off at 1, because really we're doing 1 times 10 to the n, right? Because 10 to the n is being multiplied by 1. It's our friend, the invisible 1, coming back to haunt us again, right? So anyway, so we're starting at 1, and when we multiply it by a negative number, what we're really doing is saying 1 times 10 to the negative 5th is really equal to, if we use our laws of exponents, 1 times 1 over 10 to the 5th, right? The negative means we flip it to the bottom. So what this is really saying is 1 over 10 to the 5th equals 1 over 1, 2, 3, 4, 5, yeah, 100,000. Yep. So we're really dividing by 100,000. So that means that our number is going to get smaller and it's going to be a decimal, okay? So we see that happening here. It's going 1, 2, well, 1, 2, 3, 4, 5, right? And 1, 2, 3, 4, and 1, 2, 3, and 1, 2, and then just 1, and then 0, right? Because, hey, remember, 10 to the 0 is equal to 1, because anything to the 0 power equals 1. Remember, it's our most glorious math fact. We love it. It makes everything so simple, right? So anyway, so then it goes right back up. So when we see a negative number, that means we're getting smaller, right? And then when we see positive numbers, that means we're going to add zeros back on. So we're starting here, we're going this way, right? 1, 1, 2, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5, right? Simple enough. It's just counting and then sticking zeros onto numbers. It's pretty much the easiest thing ever, or at least I think so. But if you don't, that's okay. And I'm happy to help when I come back, okay? Which is not tomorrow, by the way. I will not be back tomorrow. Anyway, so we've made out a little chart, right? So this is just a kind of a quick reference in case you don't feel like counting zeros, but we can kind of see how that exponent n is going to be affecting how many zeros we have. So let's say we want to write this number in scientific notation. The first thing we need to do is we need to identify our integer, right? Here's an integer. We can turn it into an integer, right? 1.43. Now, right now, this decimal point is right here at the end of the number. And we need it to move so that it's sitting right here in our integer that's between 1 and 10. So we're going to move it. 1, 2, 3, 4, 5, 6, 7, 8, 9. Move it back 9 spaces, right? So that means that we're multiplying 1.43 times 10 to the 9th, right? This is our place value. 10 to the 9th is just telling us what place are these going to be in. So it's going to move 9 times, 1.43 times 10 to the 9th, right? And now if we wanted to do something like small, so let's say 0.0000456, okay? We want to write this in scientific notation. So the first thing we need to do is we need to write an integer out of this, find an integer that we can write between 1 and 10. So here we go, 456. Obviously 456 is not between 1 and 10, so we're going to put our decimal there. So that means that we're trying to get the decimal from here all the way back to here. So we're going to count again. Are you ready? Here we go. We're counting. 1, 2, 3, 4, 5. We're moving back 5 spaces. Now, note, this number is less than 1. So that means that we had to have a negative exponent on 10. And we know that that negative exponent has to be negative 5 because we counted 5 spaces. 1, 2, 3, 4, 5. All right. So 4.56 times 10 to the negative 5th. So obviously, we just have a bunch of counting that we have to do, right? Right. So, now, what shall we do next? Let's do a little testing, right? We're gonna see if we can test ourselves and identify things that are written in scientific notation. So voila, here we have some problems, right? We're going to test these. We're going to see if they are written in scientific notation already. So I'm going to get out my red pen to check these, okay? Go ahead, take 30 seconds, and I want you to quickly kind of go through these in your head, maybe talk to the people at your table, and decide if you think that these are written in scientific notation or not. Okay? All right, ready, set, go. Okay, so welcome back. I hope you have your answers ready because we're about to go over them. All right, so I just want you to check yourself and make sure you understand. Okay, so 3.5 times 100 squared. Now, obviously, something is wrong with this. This base is not 10. So because that base is not 10, it does not follow our format of 1 times 10, a times 10 to the n, where a, sorry, I'm using a really fat pen for this, is between 1 and 10, and n is an integer. So this is not equal to 10. Our base has to be 10. So this is a no, not Number 1 is not in scientific notation. All right, let's look at number 2. Negative 3.5 times 10 squared. So our 10 is fine and our squared is fine, but our negative 3.5 is smaller than 1. So this one is also not in scientific notation. Now, number 3 should be obvious. If number 2 was not in scientific notation, then 3 is not in scientific notation because negative 35 is substantially more negative than negative 3.5. So this one is wrong as well. Sorry, no. All right, what about 4? 3.5 times 10 to the negative third. Maybe that negative integer is still tripping you up. That negative 3? But I'm going to tell you, it shouldn't, because 4 is a nice, wonderful problem, and it is written in scientific notation. Okay, and the reason is because 3.5 is between 1 and 10. 10 is our base, and our integer, or our n, is an integer, so we're good. Okay, all right, so yes, that one is in scientific notation. So let's go ahead and look at number 5 here. Oh, I have pink now. Didn't mean to do that. All right, so let's look at number 5 now. 0.35 times 10 to the 14th. 0.35 is less than 1, so this one is not in scientific notation. And last but not least, 1.8, so we're good there. Times 10, good there. To the 1.3, that is not an integer, so this one is also a no. So our only good one was 3.5 times 10 to the negative third. Another one you might want to think about is 35 times 10 to the first. Not in scientific notation because 35 is bigger than 10. So, no, just stop thinking about that one. Oh, I erased it. That was awesome. All right, so let's go up. Okay, so now let's talk about going from scientific notation into standard form. So according to your textbook, the weight of an Asian elephant is 5.5 times 10, I'm going to make this much less fat, times 10 to the 6th grams, right? Now that means absolutely nothing to me because when I like to think about the weight of elephants, I like to think about the weight of elephants with all of their zeros in place, right? So let's put the zeros back in place. So we're going to start with our 5.5. And what we're going to do is we're going to hop the number of times that our exponent tells us to. So we're ready to hop. 1, 2, 3, 4, 5, 6. So I just hopped the number of times that my integer told me to. So now I have all these empty spaces, which means I got to fill them with zeros. So we put a 1, 2, 3, 4, 5 zeros in that place. And now we move our decimal, the number of times we hopped, so we rewrite our answer as 5500000. Now I'm also a person who needs commas, so we'll put our commas in there. There we go. So we have 5,500,000 grams. Now, since we live in America, we don't use the metric system, so grams still doesn't mean a lot to me, but I'm assuming that 5,500,000 grams is a lot. So, you know, don't let an elephant sit on you. Now, in contrast, an ant is 3.1 times 10 to the negative third grams. Again, grams. I don't know what it is with grams. But 3.1 times 10 to the negative third grams. So, we're going to write down our 3.1. And now, because this is negative, our number should be getting smaller. You saw over here was positive, and our number got bigger. It's much, 5.5 million is much bigger than 5.5. So here, 3.1 should be getting smaller. So we're starting at 3.1, and we're going to hop 3 places to the left. 1, 2, 3, because that's how we get smaller. So we're going to fill in our hops with zeros, and now we're going to move the decimal. So 0.0031 grams. So, makes sense. The ant weighs substantially less than a gram, and significantly less than the elephant, which, frankly, is good. I would be scared of ants that weighed as much as elephants. Anyway, moving on. Glad we can do that, guys. You are really kicking some butt today. I assume. Because I can't actually see you. But, whatever. Gadzooks, I almost forgot to teach you how to put this into your calculator. So let's check ourselves up here. Not here. Nope, not there either. Maybe we have to go to the end. Yeah. Oh, Yeah, here. We're going to check these. Okay, so we started with these numbers, and we counted all their zeros and things like that. So we're going to go ahead and pop this into our calculator and then that into our calculator and make sure that they equal the thing that we started with. So let's pull our calculator up. Clearly I was doing something similar to this earlier if you look at my calculator history. Okay, so we're doing 1.43. Hello. That's the wrong one. Discard that one. Oh, cancel. Hello. Alright, this one. Okay, 1.43 times 10 to the 9th. So 1.43. Now, there's multiple ways we can pop this in here. We can either say times, and we'll use this little 10 to the, and we put 9 in there, right? Okay, and then we'll get something funny like this. We don't want any of this funny business because this still doesn't really tell us if we're right or wrong, right? What this is doing is using calculator speak to say the exact same thing we just typed in. But instead of 10 to the, it uses E. Don't ask me why, I don't really know. But we can also write it like the calculator and try to talk to it a little better, and we can use this little double E down here. So if you see I clicked it, it's highlighted in red right now. That means 10 to the, and we are saying 10 to the 9th. So 1.43 E9. So it just took out this little section here. When we plug that in, it changed our number. Now we can see that this number is very similar to the one that we had. So let's count the zeros and make sure it's the same. 1, 2, 3, 4, 5, 6, 7. 7 zeros. Let's go back to here. We had 1, 2, 3, 4, 5, 6, 7 zeros, so that means that we're doing it right. So let's go back to the calculator and we'll try the other one now. So 4.56 times 10 to the negative 5th. So we can either do 10 to the negative 5th. Oh, would you look at that? 1, 2, 3, 4 zeros. We're in good shape. It also rounded, which I think is a little silly, but whatever. Lazy calculator. So 4.56 E negative 5 also will work for us. Or you could do it the old-fashioned way, 4.56 caret. And now we want to do negative 5 is what we've been typing in. Okay. Now, if you ever are typing in multiple things that have multiple exponents, so say we wanted to then multiply this by 5, you have to make sure you arrow out of your exponent. So arrow out of it and then multiply by 5. Okay. But nope, see, and that also did a wrong thing because I forgot to multiply by 10 to the, sorry guys. I'm sure you all were laughing at me in the classroom. Okay. All right, there we go. So we're looking pretty good. I think we got it. I think we got this whole writing thing down. Okay, so let's move on. Okay, so let's get back to talking about why we think scientific notation is really useful. It's useful for things like trying to compare the size of the oceans when people give you the size of the oceans in scientific notation. Duh. So let's say I was being really complicated and just wanted to mess with you. And I told you that the Indian Ocean is, let's see, this is their surface area. So we're talking about how big the oceans are, how much of the earth they cover. So kind of, you know, back to my little, here's the earth, round. Yep, round and covered in water. So we're going to talk about just how much water is there on the earth. So the Indian Ocean is 7.49 times 10 to the 7th kilometers squared, also metric, Merca. And then the Atlantic Ocean, and I'm sorry, Indian Ocean, I meant to capitalize you. The Atlantic Ocean is 1.06. All right, pause for a second. And just like magic, all the other numbers showed up. Weird. So anyway, we want to put these in order, right? Because we just really want to know how big they are and which one is the biggest, which one's the smallest, and where they go in between. So what we're going to do is if we just looked at these numbers, well, it might look like the Indian Ocean is the biggest ocean, but it's not. I'll just tell you that right now. It's not the biggest ocean. Now, obviously that's not going to be trustworthy. And the reason is because when you start multiplying by these 10 to the 8th and 10 to the 7th, these 7.49, the 1.06, the 1.41, the 1.8, they become very, very, very small. Or the differences that they create are not going to be that much in the grand scheme of things. What really is going to make the big difference is this number here. So that's going to be the first thing we're going to use. So first, let's kind of break it down by 10 to the 8ths and 10 to the 7ths, because 10 to the 8th is going to be bigger. So let me get one color. It's going to be our orange group, 10 to the 8ths. Okay, so we have the Atlantic Ocean. It's going to be somewhere over here on this end of the spectrum, and our Pacific Ocean, because it has a 10 to the 8th, is going to be somewhere over here on this end of the spectrum. Okay, so we have 1.8 times 10 to the 8th, and then we have 1.06 times, oh, that's ugly, times 10 to the 8th. Okay, that's on one side of the spectrum. And then on the other side of the spectrum, we have the Indian Ocean, which is going to go down here, and then the Arctic Ocean. Going to go down here because we have a 10 to the 7th and a 10 to the 7th. So the Indian Ocean is 7.49 times 10 to the 7th, and the Arctic Ocean is 1.41 times 10 to the 7th. So great, we have it at both ends of the spectrum, but now we need to actually put them in order. So our first step was to look at the power. We put the biggest powers on the right, and we put the littlest powers on the left. Okay, so now we need to look at these guys now. So we don't want to look at those first. We want to look at them second. So obviously 1.41 is a smaller number than 7.49. So that means that 1.41 is less than, 1.41 times 10 to the 7th is less than 7.49 times 10 to the 7th. Okay? So we put the bottom half in order. And now let's put the top half in order. So 1.8 is bigger than 1.06, so 1.8 times 10 to the 8th is a bigger number than 1.06 times 10 to the 8th. And if you're skeptical, you could always write these out, count zeros, and spend a whole lot more time on this than you need to, but you could do it. You could do it if you're just really confused by scientific notation. But I would encourage you to keep trying. Keep at it, okay? Anyway. So, that's putting our numbers in order, all right? So you'll have some questions like this on your homework tonight. And, yeah, I think we're almost done. So hold on. So just real fast, we're just going to try one more ordering problem together. And I'll give you your numbers here. So we have put these numbers in order. Okay, so these three numbers, we want to put them in order from least to greatest. So the first thing we want to look at, you guessed it, we're going to look at the power. So here the power is our invisible friend 1. Remember, any number with no exponent on it is also raised to the first. The invisible 1, he's just checking in, checking out. We can put him when we need him, and we can take him out when he's kind of clunky. So we're going to put him in just for comparison's sake. So 1 is smaller than 7, is smaller than 9. So this, oh, I forgot one. I'm 495. And then this guy, we kind of might want to write him in scientific notation so that he's easier to compare. So let's make sure these are all written in scientific notation. So 49.7 times 10 to the first, we're good. 4.17 times 10 to the 7th, we're good. 0.047, no! bigger. That's bad. We talked about this. This number has to be 1 or bigger. Also, I lied again. 49.7 is not good either because that number is bigger than 10. So we want to make sure we write it correctly. Now we're going to drop this down 1, which means we're going to raise this guy to a 2. So he's going to be 4.97 times 10 to the second. Okay? And that means we made the decimal one. And since we made our first number smaller, that means we have to make up for it by making our exponent bigger. Okay, so 4.97 times 10 to the second. Here, we said that one is fine. And now this one, we're going to move this back, right? We're going to make it 4.7. So it's moving back 2, which means we need to make this number 2 smaller, right? Because we made our number bigger. So in order to make up for it, this guy is going to have to be smaller. So it's going to be 4.7 times 10 to the 9 minus 2, because we moved it 2 places, 10 to the 7th, okay? And then 495, I'm going to write that as an integer between 1, or as a number between 1 and 10, 4.95, okay? So it's moving 1, 2 decimal places times 10 to the second. All right, so now we can really do a heck of a job putting these in order, okay? So our 2's are smaller than our 7's. So we're going to put those on this side first. Okay, and then put the other ones that we have. All right, but now we need to compare our individual numbers. So 4.97, 4.95. Well, 4.97 is bigger than 4.95. So 4.95 times 10 squared, 4.97 times 10 squared. And now we need to compare our 10 to the 7ths. So we have a 4.7 and a 4.17. Well, those are already in order because 4.17 is a bigger number, or smaller number than 4.7. So we can rewrite those. And voila, we've put the numbers in order. It's like a miracle. Okay, so if you have any questions, you can rewind this video to where you need it to be, or you can ask your friends. You know I like you to do that, and I believe that you all are very smart people, and I know that you can figure it out. So I'm going to go ahead and give you an assignment to work on. You can work on it for the rest of class now. And then this will be your homework, and I will check this off, plus the assignment I'm going to give you tomorrow when I come back on Friday. Okay? So, your assignment is... Okay, there's your assignment. It's in your textbook because the textbook gives perfectly good scientific notation problems on page 424, and you're just going to do 11 through 39 odds. So since I gave you the odds, the answers are in the back of the textbook, and you know how I feel about that. I want you to check your answers. I want you to figure out what you do and you do not know. So come back with your questions, give your homework a shot, and I wish you the best of luck. Have a great day, guys. I will see you on Friday.